podcast for developers by developers, where we discuss technology and trends in industry. I'm your host, Tony Monkolsmai. We've talked to a lot of people who work on the Argonne Aurora Supercomputer, and today we're going to revisit where things are at in terms of the capabilities and the applications that are running on the Aurora Supercomputer today. Scott Parker is the lead for performance tools and programming models at the ALCF. He received his BS in mechanical engineering from Lehigh University and a PhD in mechanical engineering from the University of Illinois Urbana-Champaign, my alma mater. Prior to joining Argonne, he worked at the National Center for Supercomputing Applications, where he focused on high-performance computing and scientific applications. He's been at Argonne since 2008, and he works on performance tools, performance optimization, and spectral element computational fluid dynamic solvers. Welcome to the podcast, Scott.
Oh, thanks, Tony. Happy to be here.
So you are leading the effort to port a lot of the applications from wherever they were coming from before and make sure they're up and running on Argonne. So can you talk a little bit, just high-level background, what's that landscape look like and how's that effort going?
Yeah, sure. So I'm one of the folks that's leading the effort. There's two other people working with me, Chris Knight and Tim Williams. And the reason we have so many people is we were working with a larger number of applications than we've really worked with in the past. Today we have about 40 applications that we're working to get ready for Aurora, with the goal to have, the applications ready to run when the hardware and the machine is ready to go. So it's been a pretty, long process. This will be the first, GPU-based system that Argonne has deployed. It's really the first Intel-based GPU system, at this scale in the world. So there's been, a lot of challenges. First, just getting the applications ready to run on a GPU system because not all of them were there. Some of them were set up for other GPU, platforms. And then, working with Intel to make sure that everything is working correctly on the system.
Yeah, and for those who did not catch our old podcast, we did talk to Chris Knight and Tim Williams in the past. So feel free to go back and listen to that. Little plug for our podcast from last year. So yeah, you mentioned some of the stuff were coming from a CPU-only arena, and some of them were coming, I'm assuming, from NVIDIA. That would make the most sense. Can you talk a little bit about the efforts? What are the challenges when you're coming from a CPU landscape? And then how are you guys tackling those? Like what kind of libraries you're using, et cetera? And then similarly, coming from NVIDIA, what are the challenges there when you're coming from the NVIDIA, SDK world?
Yeah, so, these scientific applications, some of them have been around for 20, 30 years. They've gotten to be quite large and they're very technically complex. There's a lot of, complex mathematics and modeling that's baked into them. And so, changing them is a non-trivial effort that takes, people with a lot of experience, years to do. So it's a long-term effort, and moving a code like that to a new platform is challenging for a lot of reasons. One of the challenges, first of all, is that we're deploying an Exascale system. This is orders of magnitude more powerful than some of the machines that these codes have been running on recently. And so one of the things with this new larger scale ability to compute is the codes really the scientists want to do new things, and so they have to write the logic into the algorithms into the applications in order to do that. So really what we want to see people doing on these larger scale systems, the reason we're investing all the time and money into them, is really to do breakthrough science. And in many cases that means the code needs to evolve to be able to do new things. So that's one of the first challenges for the science team, and that's primarily on the shoulders of the science team. And so, at Argonne, we partner with a lot of research groups around the world at universities and other labs to do this work, and they often do a lot of the lifting there, though we do have staff on our side that can contribute to that. The next step is really figuring out, how are you going to program your code to run on Aurora, right? So Aurora is an Intel GPU-based system. If you're running on a CPU-only machine before, you're probably using MPI and maybe OpenMP as your programming models. And we certainly have MPI on Aurora. That's something, virtually every code is using. OpenMP is an option. That's there's a, in the later versions of OpenMP, there's directives that let you, tell the compiler to offload code to run on the GPU. But there's also codes that were running on NVIDIA platforms using CUDA. And that's not something, CUDA is proprietary to NVIDIA. And so that's not something that we could, allow people, have people use right off the bat on Aurora, though we do have an approach to that we've been working on. I'll talk about that maybe a little later on. So, people picking a programming model, and in many cases, people want to make sure that the time that they invest in preparing their code is usable somewhere else. So they want it to be portable, not just run on Aurora, but they want it to run on CPU machines, and they want it to run on NVIDIA GPUs and AMD GPUs and whatever else might be coming in the future. So people spend some time, looking at the various programming models. And in our case, we have a number of them that people can choose from. So there's, as I mentioned, OpenMP. There's SYCL, which is something that, Intel's invested a lot in their oneAPI compilers. And so that's an open programming model that's portable. Beyond that, there's several DOE based programming models that have a real focus on portability, including Kokkos and Raja. And so we have a few codes that are using those too. So we have a broader diversity of programming models and approaches that people have taken over the last several years to get their codes ready to run on the machines. And most people weren't necessarily familiar with those programming models before, and certainly their code in many cases wasn't written to use them. So there was a lot of work that had to go into getting their codes into those frameworks, ported and working. So there was a lot to do there.
And for those different frameworks, how did they decide which one to use? Obviously, if you were coming from like CPU OpenMP, it was probably an easy decision to say, let's try a GPU offload OpenMP. But how do they decide between maybe using a oneAPI UXL base stacked versus Kokkos, Raja? How did you guys guide people to make that decision?
Yeah, I think each code team, worked through this and on their own. Like you said, if you were using OpenMP, that was a natural path. For Fortran codes, that is probably the only really viable path, unless you want to rewrite your code into C++. But for codes that were in C++, and there's more and more of those today, they had options, which is nice, but it also makes life harder to have choices sometimes. And so, some codes were already using Kokkos, and so for them, it was stick with Kokkos. Um, and then I think if you're people who are using CUDA, in many cases they look to SYCL because while the semantics, the way you express it is different, the underlying logic behind CUDA that's expressed and is expressed in SYCL have a lot of similarities. So it's sort of a natural migration, I guess. And there's some tools that Intel's provided, Cyclomatic, that can automate part of that process and make it a lot easier. So a number of teams went down that path. But in many cases, they sat in, in some cases, they tried different ones. They wrote little test codes in several different programming models and sort of, decided what they like best. And some of that is left just to the person, the individual developer, right? They may just feel more comfortable in Kokkos because it fits better with how they think about things, and so they went that path. Other people, liked OpenMP because they were familiar with it, and so they went that path.
Yeah, and that totally makes sense. As a developer, I would definitely want to have that option and just choose what works best for me. For the over time, I guess you have actually a paper that you'll have released by the time this podcast comes out, but it shows the trends over time of where you guys were at in 2022 versus where you're at today. Kind of Q2 of 2024. And you can see, and we'll put this up on the screen, excuse me. You can see kind of the trend of going from some small set of applications run to almost, I'll say, all of the applications are at least looking viable to run. And looking at the sheet that I've got pulled up here, it looks like, I don't know, 60% of the things are running in a very good way from your estimation. Can you talk a little bit about that trend over time and what that experience was like in terms of the porting, all of the challenges you faced there?
Yeah, so it was a multi-year effort, and like I said, there's many steps that people had to go through, both in terms of getting their physics incorporated into their code, choosing a programming model, porting it, and then there's a lot of work to do to make sure that it runs correctly. You do all that work, change a lot of lines of code, you're going to introduce bugs, and the Intel compiler frameworks were new, so they hadn't been tested as extensively as you have on the x86 platforms, and so there were some issues there too that we had to work with Intel. So it was a multi-year effort to work through these various stages, And I think it can be challenging because there's a until you get the last bug, the last line of code written, and the last bug resolved, your code doesn't run. So you can, in cases, spend many years working on something where you don't achieve success until that last day, right? And so one of the things we did, like you said, is we tracked this, kind of carefully throughout the project so that we could understand, how things were going, because there's a lot of risk with new hardware, with new applications, with new, programming frameworks, that things won't mature and that they won't come together. And that's one of the things we were very concerned about when we started this project. And so we put a lot of time into, making sure that were we doing the things that needed to be done to ensure success. And so, what we were able to do is track that over time and see that, yes, people were making progress. And, for a while it was very, a lot of codes weren't running. They had a lot of issues, and we were, just hammering down those bugs one at a time. And as soon as you took care of one, you would find the next one. So unfortunately, it tends to be a sort of incremental process that way. But then we started to see, we kind of color coded things like red was not running, that's bad. And green was running, and that's good. And we started to see more greens, pop up. And performance is obviously a concern. One of the reasons we have these machines is to be able to compute very fast. And so we want the applications to run fast. It's not just sufficient to run, but they need to run well. And so we had a couple shades of green, ranging from light green to medium green to dark green for, our assessment of where their performance was at. And the first few started with a light green color, meaning, well, they're running, but maybe not where we wanted them to be. And then over time that, improved as people understood the architecture better. They made changes. We worked with Intel a lot. We had hackathons, we had workshops where people got together and they looked at, the various lines of code in depth and, in some cases dug into the assembly to understand what was going on and really tune those applications to today. We see, a large number, over half of them are performing very well. And like you said, almost all of them are running. And so we're pretty happy with where we are. I mean, there's always room for improvement, but I think for this stage, for a brand new platform, we're really excited about having this many applications ready to run and run well now that we have the hardware on the floor.
Yeah, and we'll probably flash up for our video podcast watchers. We'll flash up kind of the list of applications so those people can see where they're at based on the paper that you guys are going to release. And it does cover a lot of different scientific domains. I think one of the biggest things that we've tried to reinforce when we talk to people from ALCF about Aurora is all of the science that you're going to be able to do on this platform. So we've got astrophysics, fluid dynamics, material science. Obviously, AI is starting to come online, and people are talking about that. I know that we're going to talk a little bit more about Aurora GPT in the future with some other guests. So I think you guys said you have 40 plus applications already running on the Intel Data Center Max GPU. So the actual effort from porting these applications is now they are running on GPUs, or is it still some of them are running on CPU only?
No, those 40 are all running on the Intel GPUs. We have a few other codes that people run on the CPU only, but 95% of our computing power on Aurora is on the GPU. So if you're not using the GPU, you're really not getting the most out of the system. Some codes applications have sort of a workflow where a big application does a lot of the number crunching, and then there's a smaller application that comes in and does some analysis and things like that. And so those are okay to run on the CPU. And we do have the Sapphire Rapids with the high bandwidth memory, which is sort of new in the CPU area. So that applications that are memory bandwidth bound can do pretty well on the just on the CPUs themselves. But it's really important to utilize the GPUs, and so virtually all of our applications are focused in that area.
So let's talk a little bit about scaling. Obviously, we're talking about a supercomputer, and the things that people always want to know about are how far have we gotten to where we feel like we're at scale. So again, looking at your paper, it looked like you had some workloads that were running on a couple thousand nodes. Can you talk about how many of those do you expect to get there? What's your target there? And how close do you think you are to that?
Yeah, so that's ongoing work. Aurora has about 10,000, a little over 10,000 nodes. And typically on our past platforms, most of our applications would run on 20 to 40% of the machine in a given run, so that really to get the performance you need to use a big chunk of the machine. And there's a lot of different people running. It's not typically used just by one science team. There's dozens of science teams, and so they're all kind of taking turns and using a fraction of the machine. But generally we encourage people very strongly to use at least 20% of the machine. Otherwise there's other resources that they can compute on in other places. So really what makes the supercomputers super is the all of the nodes working together to give you more power than you would get in a single rack or a single server. So it's really important that you get that scale, and it's a process. I mean, this is something we've done for years, right? This isn't new to us. Scaling applications up to tens of thousands or hundreds of thousands of processes is something we've done before on past systems. But every system's different. Every system has its own unique challenges, and these are all first of the kind, first of their kind machines. We're not deploying architectures that have been put out and tested in the field in other places. So everything you do that's new on them, you get your first hardware, it's one node, and you work things out there, and then you get 64 nodes, and you work things out there, and then you get 1,000, and you work things out there. And so it's an incremental process as we get more and more of the machine available to us, to run higher and higher. But I'm fairly confident, like you said, we already have a few codes that have run at 1 to 2,000 node scale, which is pretty close to where we want most of them running. And I think the fact that a few are able to do it means that they're smoothing the path for the rest to follow, I think.
And when you're doing this enabling, like from the one node to the 64 node to the thousands of nodes, is the biggest challenge load balancing the communication, or load balancing like the storage, or load balancing the compute? What's the biggest challenge there?
So the biggest challenge, there's several challenges, but load balance is often one of the areas that trip people up. So if you're running an application, you might have one part of your domain. Let's say you're doing a fluid dynamics solver, right, and you have a wall that you're simulating. Some of the field is along that wall, and you have to treat that differently than you do in the middle of the fluid. And so that could either be more work or less work. And so the node that's running that part may run faster or slower than the rest of them. And if there's one node that has more work, let's say twice as much work as everybody else, then often the rest of the nodes have to, they finish their computing and they stop and wait until that one catches up. And so you lose a lot of your, efficiency that way. And so one of the things the teams really spend time on is, how do they get that work distributed very evenly across, the full machine to allow it to scale. The other, challenge is, what we call strong scaling versus weak scaling. So if you want to run a bigger and bigger problem, that's sort of easier because you keep putting more work on the machine as you get more nodes. But if you want to run sort of a fixed size problem, let's say you want to simulate the weather on the Earth, right? And the Earth doesn't get bigger, right? It's a fixed size. And so you want to do that faster and faster, right? And so you bring in more nodes, but the amount of work per node goes down and gets lower and lower. And then these inefficiencies creep in, right? Like the offload to the GPU has some overhead, the communication has some overhead, and so those inefficiencies start to eat away at your overall efficiency, and it gets harder. So that's one of the areas people have to work to really optimize the performance.
And so right now, the things that are scaling to the most number of nodes, are those the ones that you mentioned the problem size is just getting bigger, or is it just kind of a mix of whoever happens to get there first?
Well, it's a combination, but certainly the ones that have really large problems and they can continue to make their problems bigger, I think have the easiest path. The weather modeling folks, for instance, have a hard time because they just want to do it faster, and they're not making their problem bigger necessarily. They just want to do it faster, and so that's a bigger challenge. And there are a number of problems like that. That are just difficult to scale out at a certain point, and so they just require more work to try to change the algorithms, or make the communication more efficiency, or really hammer down that last little bit of load imbalance.
All right. And so what is next for you guys? You've got these 40 applications in a decent state. Obviously, you said you're going to tweak them. You're going to make them faster. You'll get the things up and running that aren't currently running yet, if there are those things. But what are you looking forward to in the next Q2, Q3, Q4 of this year?
So, the machine is on the floor at Argonne. We've been able to run things at that scale, but we really want to scale up and we want to get people, not just, out of the development phase and into what we call the production phase, where they're really starting to tackle their scientific problems and get new breakthrough results. We want to see people putting papers out saying, hey, we discovered this new thing running our code on Aurora. And then beyond that, 40 codes is a good number, but, on past machines, we might have 1 to 200 different codes running, over the life cycle of the machine. And so there's, a lot of other applications out there that, we haven't yet had the opportunity to work with. And so that will be our next step, is kind of the next wave of codes.
And do you think that based on your experience now, is that going to be a lot easier? Are the tool chains getting better? Are they being more stable? Obviously, it's been a couple of years. Hopefully, we fixed some bugs for you from our compiler and our stacks. Are we at a point where you feel like we're in a good space there to do these migrations faster?
I mean, it's always a lot of work, but yeah, I think it will be significantly easier. I mean, people can look at the approaches that other teams have taken and understand the trade-offs from their experience. And then, it's more easy to choose their path. The tool chain is, dramatically improved from where it was, several years ago. So I don't think a new application will face nearly as many issues. So it should be easier, and we have some new things going into where a lot of codes are coming from CUDA, and one of the things we did was we implemented a version of CUDA. There's a variant of CUDA called HIP for AMD GPUs, and we've actually worked with AMD and other folks to make that available on Aurora, and it's still sort of experimental, but for codes that are written in CUDA or HIP, we hope to see them able to take advantage of that.
So to be clear, in this case, typically when you use HIP, you're going to run it. You're going to take a CUDA enabled program and you're going to run it on an AMD GPU. In this case, you're actually using the open source HIP and trying to translate that into an Intel GPU.
Yeah, so the code stays the same. The user code stays the same, but it can run sort of out of the box on an Intel GPU. And we have a number of codes that are able to do that today, and we're looking forward to working with more. And so the idea is just to give some portability to folks that have chosen that programming model across, the different GPU platforms as an option. It maybe is not, the one that's the most mature on Intel GPUs today, but it is an option, and we hope to see, more applications, take advantage of that if that's their chosen path forward.
Is that open source? Is that something anybody can look at?
Yeah. Yeah, it's open source. It's on GitHub, I believe, and so folks can go and download it and try it out, and put it on an Intel GPU and see if it works for them. And we have a team here that's continuing to develop it. So if there's issues, they can probably help with those.
Oh, that's interesting. That is one I have not heard of. So that'll be fun. I'll have to go check that out. Okay, so I think we're almost out of time, and what I always ask people is what they're looking forward to in the next couple of years. So you are a mechanical engineer, you do computational fluid dynamic solvers. Is there a particular application? Is there a particular use case that you are most excited about getting running on Aurora?
Honestly, there are so many different things going on. It's really hard to pick a favorite. We have so much invested in all the different codes that, I'm really just looking forward to seeing a lot of science teams being able to use the resource, to get new things, make new discoveries. I mean, that's really what we're putting these platforms out there for people to do. And it's been a long road to get there. We get lost in the technical details of fixing this bug or, working through this issue. But the end result is we want to see people running. And I think we're getting close to that stage. So that's what I'm really looking forward to.
All right. Well, thank you, Scott Parker, for joining us.
All right. Thank you, Tony.
And thank you, our viewers on YouTube, for watching. And thank you, our audio listeners on Apple Music and Spotify. And I hope you join us next time when we talk more technology and trends in industry.